So my name is Raynes Brown. I work for a company called Eurotech. We're located in Northfield, Ohio. We're a weird company from the perspective of we are kind of a semi-distributor and a manufacturer. We manufacture heat shrink. We do wire and cable in terms of distribution. We do tape, especially equipment. So we're really intertwined, let's say, in working and helping out harness manufacturers do coverings and cover their harnesses to prevent all the bad stuff that we don't want. So that's kind of who we are. We're in a really unique spot where we get a chance to see the entire thing from the perspective of making sure moisture protection, all those kind of things are in place. I've been working with heat shrink tubing especially for about 25 years. I'm still 18, but I've been doing this for a long time, so I have a really good idea as to kind of how it works. I started in development, where one of the guys who did all the formulations, go through, find out what polymers we need to use, go through product development, go through the whole process, go through application, did marketing, did sales, and I'm kind of back in engineering where I started. So that's a little bit about me. The first thing I'm going to say, thank you all very much for coming here to hear me talk about this. It's something that I really like talking about because I think it's very important, and I think it's just as important to everyone here as well, because you're here listening to me with regards to covering your harnesses, especially your splices, to prevent water, moisture, and all those things from ruining everything that's going on at the back end. So thank you all very much for coming in and listening to me. So, essentially, what I'll be talking about today is how do we ensure that when we put together a splice in a harness, we keep it protected from the environment. We know there's the mechanical side of things. I'm not really going to touch on the mechanical protection. We're talking abrasion, those kind of things. I'm not going to talk about that. We're going to talk a little bit more about how do we ensure that water, moisture, and all those things do not get into the back end of your sensors and all the fantastic stuff in the back of your car by traveling through a splice that was not properly protected to wreck the rest of the vehicle and your harness. So that's really what we're going to be talking about today. Few things. Questions-wise, I'd love to answer questions. However, if you can allow me to kind of go through the quick presentation, then we can have questions later. That way, we make sure, because we could probably get talking about stuff because everyone really probably has some specific challenges, let's say, with splicing that they probably would want to ask a question about, and we could get talking about that, and I'd rather we just kind of finish the presentation first and then we ask questions later. So that's kind of a little bit of the housekeeping. So where we are right now, last year, one of my colleagues, his name is Paul Wiskowski, he's going to be seeing this video. He did a presentation on protecting, not necessarily protecting, but kind of showing some of the problems that we're experiencing today with regards to moisture wrecking our wire splices and our harnesses. So where you left off last year was really talking about some of the mechanisms by which failures do occur. So what I want to do is kind of quickly go back through what some of those failures might look like. So what we have here is kind of a picture of like corrosion just by having water going in a splice that's not properly protected, or the heat shrink that they're using to protect that splice is actually ripped apart or something. But what it's showing is that this is kind of one of the, and these are real pictures that was taken from real wire harnesses from real vehicles. So, we showed a little bit of, okay, this is kind of what that might look like. We talked a little bit about as well, the terminals and eyelets, those not protected as well, what they look like because of water and moisture. Went through that. Other thing that, and we talked a little bit more about, if you don't seal the splices, what that looks like. So I just kind of want to refresh. This is kind of basically where we're coming from. This is really the end result in terms of what we see today. But there's backside of it where we have, again, some of our sensors and all those fantastic things at the back end that gets wrecked just by having water travel up your splice into those kind of things. One of the things we also show is kind of how this kind of works a little bit. Yeah, we know the obvious where you're driving on the road, it's raining or it's snow, we get water into those things. We know the obvious, but they also have capillary action that occurs as well. And what we did here was to kind of demonstrate to say, okay, if we get like a cable or wire, and we strip one end, and we stick it in some salt water, and we put it in first day, obviously everything looks good, but we start to see some corrosion. We start to see some corrosion taking place like within 2 days. And this is what it looks like after 2 weeks. No, this is salt water. So, you know, it's obviously planned to kind of show what happens if you're living in Toronto, where I live, where you have salt that you put on your road to, in the winter, for example. But this is kind of what happened. And I'm going to come back to this picture later because this is an interesting picture. But this just shows kind of, again, what would happen if you have this here in this situation. Eventually, within 2 or 3 weeks, you're going to start having a problem where your splice is going to start getting corrosion and all those kind of things. So again, the goal here is to ensure that we can protect this. There's a few things I'm going to go through. The first thing is I wanted to do a quick overview of a typical wiring harness. And there are probably a lot of people in this room who knows a whole lot more about a wiring harness than I do because I've never actually designed a wiring harness. But this is basically a schematic. And what this kind of shows is like the different, back here. This shows kind of like the different parts of the harness. So let's assume we start from our connectors. So we're moving back, we have our connectors. We have inline splicing, just because, again, we kind of have to make sure we take, you know, different wires and cables and put them all different places. We have, you know, just terminal connectors, connector and terminal, sorry, inline. Then we have end splices, which we'll probably cover with end caps or some form of a cap. We have longitudinal water blocking areas where you have, you know, wires going through your firewall into your vehicle. We have all the back-end stuff we're talking about, or radio and audio, and we even say TV because we know all those things are in vehicles. So this is kind of what a typical wire harness looks like. It's very simplistic, so we understand that someone is going Raynes, like, but it's very simplistic. It's just a matter of showing the different areas. So with that wiring harness that we just showed, there are a lot of different things going on. We have areas where it's wet, we have areas where it's dry when it's sitting in your vehicle. So if we want to protect, say, the dry areas, we're talking interior of the vehicle for the most part, you know, we can use a single wall heat shrink tubing. What that is, it's a tubing that doesn't have any glue in it. And what that does is just provide mechanical protection for that splice. So, and it helps with, you know, strain relief and all those things when you're moving, you know, jumper cables and jumper harnesses and all those small things going in the interior, let's say, of your vehicle. But this, I bring this up because this is kind of important from the perspective of we still have dry splices. And the whole idea is to ensure that we protect all splices. The good news, though, is with the dry splices, it's not as critical, let's say, because of where it sits. And then we have the dual wall adhesive tubing, which is really for the wet splices and the areas that kind of sit outside the vehicle. And this is kind of where we start worrying about water and moisture and the environment and all those kind of things. And this kind of go back to some of the pictures we showed earlier on with, you know, terminals and wires and cable and everything looking green and yellow just because of what's going on. So this is kind of what the dual wall shrink tubing does. Then we have other instances where we have specialty products that's used where you have splices in areas that it's just really difficult to seal. And someone here might be working with a splice in a heavy truck and bus or something like that where you have, you know, some 10 gauge 4-gauge cables versus, like, you know, some 20 gauge and some 18 gauge on the other end. And it's just hard. It's just almost impossible sometimes to seal. So you have to use specialty type sealants, liquid sealants. You have to use adhesives. You have to use enhancers, let's say, to ensure that you can seal those splices. So that's another part of the whole splice sealing process that we have to take into consideration when we are going through the process of sealing splices. Now, when we're doing this, there are some considerations that we must have. And we're talking about, you know, the temperature that this splice is going to be, or this harness is going to be operating under, or the splice itself. Because, like, we know if we're talking about some EV type applications where we're talking up to, I don't know, 100, because of, you know, electrical current and all the stuff that's going on sitting in Arizona in August 1st, temperatures of up to, I don't know, 120, 130, 140. So you've got to make sure you take that into consideration when you're designing your splices and the shrink tubing and all the things that you need to do to ensure that you protect that splice. Talked about environment, end splice, sub splice again, if we're going to make sure we start adding other things to, for example, you know, we send our car out and then we need to have other things that we need to add after the fact that it gets to the dealership. We've got to make sure we protect those sub-splices. We have to think about the electrical needs, what kind of voltages we're working with. We're talking about just a conventional, or we're talking about, hybrids, those kind of things. So all those matter in terms of when you're designing your splices and your the harness manufacturers, to ensure, again, we can protect them. So we're starting to get a little bit more into kind of what the crux of why I'm here talking to you a little bit. So we're going to talk a little bit more now, let's say, about the splice design itself, how it's constructed in terms of ensuring that we can provide the protection we need, some of the sealing mechanisms that exist. We're going to select tube in a little bit, just so if someone has to select a tube for the splice that they need to cover, kind of how we kind of quickly go through it. And we're going to talk a little bit about some special situations where that's going to require us thinking outside the box a little bit, which is not going to be in line and kind of easy, let's say. It's going to be a little bit more thoughtful requirements to ensure that we can seal those splices. So when we're designing splices, we know that, the OEMs, the harness designers, they've been trying since I've been in this business to try and design out splices. And I know we're at the stage right now where they're starting to get close, and that means because we have had conversations with some of the OEs, and especially on the EV side, where they're trying to figure out ways to say, hey, look, we got to get rid of some of these things. That's the bad news. The good news, though, they've been saying this for 25 years, and they're still doing it. So my gut is telling me it's not going to change tomorrow. But the design considerations are important. We've got to look at the complexity, like we talked about. We've got to talk about wire count. How do we design a splice to ensure that we have the wire count matches what we're trying to do? We don't want to have 15 wires on one side and 2 wires on the other side. We're trying to balance those kind of things. So we have to talk about the cross-sectional area again, and those all go together because they all, at the end of the day, ensure that we have what we call a balanced splice, and it's a lot easier to seal. Some other design considerations that occur, like if it's not done properly, failures can be very, very costly, because I'm not sure if anyone here has ever tried to get a wire harness and rework it. It's not fun, especially for something that might be a splice. so it's or a piece of heat shrink tubing. So that's of a challenge. And it's also difficult to diagnose. A lot of times, what's the problem? And we can't find it, and we're searching, we just can't find it. So those are some of the things that matters. And it's also difficult to repair, because just imagine I'm trying to take a harness out of a vehicle if you have to get to the point to try and repair it. It's just costly. So for us who are designing harnesses and working with harnesses and get these into vehicles, and understanding that if we have a recall that it's going to be on my dollar, we want to make sure that when we do these things, they're done properly, correctly, and it's something that we're comfortable with. So this is pretty important in terms of the wire count. So when we design like a typical splice, if we go like wires on both sides, we have our splice in the middle, wires on the left side, wires on the right side, let's say. Wires, 1 to 4 wires, it's fairly vanilla. It's not too difficult to manage and to seal and all those kind of things. So that's pretty good. Then when we start getting to a little bit more complexity, where we have wires of 5 and 7 wires now, that's starting to say, okay, we can probably still do some of this. The challenge, though, is that, we got to think a little bit more. We got to start messing around with, ovens and temperatures and all those kind of things. But when we start getting into more than 7 wires, that's kind of when we start pulling our hair out, because that's where we need enhancers. We need to go back to whoever designed that splice and say, okay, can you guys redo this to make it balanced, all those kind of things. So this is actually a big deal. So the point here is that I'm not sure if anyone here is designing splices, but the whole idea is, from a sealing perspective, it really, really helps if we can figure out a way to try and get this thing to use the least amount of wires. I know that's not easy, and to make it as balanced as possible, meaning the same amount on both sides or the area. We'll talk a little bit more about that in a minute. So let's talk a little bit more about how we design a splice. We know a typical cable, we have our outside diameter and radiuses and all those fantastic things. But there's a simple equation that you can use, let's say, to make this. So we know typically we have the real area for circle looking into the splice itself. And then we know we can also use mill circular area. And what that is like doing thousandths of an inch to kind of make round numbers and easy numbers to work with. So if you take your real area and you divide that by the mill circular area, that's going to equal, and you go through diameters and do all those kind of things, it's going to be equal to pi, because we still work with the circle, pi by 4. Pi by 4 is actually, works out to be a constant of 0.785, I don't know, some number. We just run it off to 0.8. But if you want to find your full area of that, and this is important actually, if you want to find the area of that cable, you just do 0.8 times whatever pi r square, whatever your number, you're good. You find the area of that one cable. Now, when we're starting to put a lot of cables together, all we got to do is just add all the different areas and multiply it by 0.8. So what that does now, it tells us the area that we're working with for that splice. Okay? And we're talking about both sides now. The reason why the insulation is involved still is because we have to get the tubing over the insulation still. So even though we strip off the ends, we're not working with the ends alone. We're still working with the entire cable that includes the insulation. Well, this is an easy way for us to do a quick design, let's say, of a splice to ensure that we have a really, really good idea as to what we're working with in terms of sizes and diameters. So that was that. So if we talk about the construction now, this is actually extremely, extremely important in terms of construction. The whole idea is to ensure that when we get an adhesive heat shrink tubing and we put it over a splice and we shrink it down, we want to get the adhesive to kind of flow in between any gaps and fill that up. At the end of the day, it's nice to have, the insulation matters in terms of sealing splice, but it doesn't really matter that much. Because what we really care about, because we know the insulation is going to cover these areas, right? So if we get our tubing to shrink down and bond and do all the things to the insulation of the cable itself, I know we're good. What we have to do actually though is get the adhesive to flow in between these areas and fill that up. And that's the reason why we always ask for a minimum length between the insulation here and the splice nugget. And that's about, oh shoot, what am I doing? That's about 3.5, it's a 3.5 plus or minus 1.5 millimeters. And the reason again is to get the adhesive to flow into these areas, because at the end of the day, you can actually at some point, like I've seen areas where the tubing itself kind of gets moved, the adhesive is still in place, and the splice is still sealed. That's not what we want, but it does happen. But the key here, when we're trying to design splices, is to ensure that we have enough gap for the adhesive to flow in there and fill it up. That's the whole idea behind that. We have instances, obviously, where it's not done properly, and we'll talk a little bit more about that. But like areas like this, for example, where it's a little smaller, we don't want that. But we see those again. But the whole idea is to again try to get it in this area. And there are different ways of doing it, like we talked about. You can weld it, you can ultrasonics, we can solder, you can do all those kind of things. But again, at the end of the day, we're really trying to ensure that we have enough space to ensure the adhesive flows in and fill up the gaps. Now, areas where construction is not as good as we'd like we talked about before. Yeah, so we have area where one side of the gap is too big, the other is a little bit, not what we want. We have areas where we have what we call flyers. The issue here with this one, this is a big deal, because the heat shrink tubing, once it's under heat, it gets a little bit softer. So when you're shrinking it down, if you have a wire that's sticking up, it's going to, like we call it poke through, it's going to poke right through the tube, and then that's obviously going to create a dielectric problem. And eventually you can, again, start getting corrosion on that one cable or one strand that's sticking out, and eventually we start getting water, capillary action, start moving down and start messing up. So those are things that has to be taken into consideration. I try not to read what's on here. I hope everyone probably can read it, like if I can get in a little bit more if need be. Yeah, so we talked a little bit about exactly how this worked before. Whole idea is to get the tubing over your splice, shrink it down, and have the adhesive flow and fill all these gaps in here to to ensure that we have the whole thing sealed up. So that's really kind of how the entire thing works. So the next thing that I wanted to touch on is tubing selection. When we're selecting tubing, we look a lot at the diameter, inside diameter. We look at stuff like wall thicknesses, we look at lengths. We look at, those are the things that we look at on the tubing itself. But what's more important is when we look at the splice itself is we need to find a tubing that we can easily work with, that it can easily fit over the tube, over the splice, I'm sorry. Enough length so we have enough adhesive on both ends to kind of flow. We don't want it too long sometimes if we don't need to, if we're having an oven where the shrink area is not as wide as we like. We're using a heat gun, you can go as long as you want, it just takes a long time. You have to look at your process. You have to look at a lot of things when you're actually trying to select a tube. But some easy rule of thumb for selecting tube is just look at your area and go, okay, I'd like my splice to fit into about 80% of the tubing, 75% of the tubing. So let's assume your area, I don't know, 1 squared, 2 squared millimeter. All you want to do is just find a tubing that's, I don't know, a little bit bigger, let's say, to fit in there. So when you shrink it down, it fits in nicely and it goes over both sides. So those are like really simple rule of thumb. As you know, and again, we can go into math and all the details of that. And there are a lot of tubing selector programs and things out there, and they all work because we have one. But quick rule of thumb is like 80%, stick it in, we're good. 75%, we're good. And I'm trying not to bore everyone with some of this technical stuff because like the whole idea is trying to make it as simple and as possible. And this kind of get a little bit more to some of the language, let's say. You know, inside diameter, obviously it's the inside of the tube. Without restricted, when then fully shrunk or fully you don't have any restriction in there, that means you don't have any substrate in the tube and you fully shrink, so that's your fully recovered diameter. A wire, a cable, or a splice in there, then you start having restrictions, so you have to start taking those little things into account. So like we talked about, we want to select a tubing that's going to easily fit over the largest side of the cable. We talked about calculating the total area. We want to make sure that we don't force it through, so we don't start messing around and damaging heat shrink or wires and cable. We also want to make sure, if need be, we go to a larger size. That's always okay as well, depending on what you're doing. So those are just some of the basic ways of selecting. Like we said, 20% of your diameter is okay. Something else that's important is the shrink ratio of the tubing. What that means is every once in a while, even though someone like myself would be happy to get a splice that's 100% balanced 100% of the time, that's not possible in the real world. So sometimes you might have a splice where one side you have, like, say, 4 cables, the other side you have 2. Because of the difference in diameter, one of the things we got to do now is choose a tubing that's going to cover both the larger side and the smaller side. So we have to choose we have to look at what we call our shrink ratio. And the shrink ratio now is the ratio of the expanded diameter versus the recovered diameter. Now, again, like we talked about, is fully non-restricted shrinkage when we're doing that. So the whole idea is to make sure we can easily fit over both sides and we can shrink down to make sure we cover the smaller side as well as the larger side. So that's why the shrink ratio matters. In splice sealing, a lot of times we tend to go to 4:1 shrink ratio. And the reason for 4:1 is just because, with different size of course, it's just because we're always fairly comfortable that with the higher shrink ratio, we will be able to cover both sides of the splices comfortably for the most part. Sometimes, again, if we're finding on the small side we can't quite get down, even though the adhesive flows and does all the things, we drop one side if it can work on both sides. Sometimes we look at trying to go to a larger ratios. Those are fantastic. The issue here is making a higher shrink ratio tubing is a lot more difficult. So from our perspective, we always try to make sure we get the sweet spot that works, but special applications require doing special things, and that includes doing a higher shrink ratio sometimes when needed. We also talk about wall thicknesses. The value of wall thicknesses, there are some things that's required. We talked about the electrical requirements, because sometimes you need in a situation where you have 600 volts, the wall thickness is what provides most of the electrical requirements, the dielectrics and those kind of things, in addition to the other parts of how you design and develop the tube. So that's a big thing in terms of making sure the wall thickness matters. The other part of it too, you kind of pay more attention to the recovered wall thicknesses, because that's kind of what you're working with in the real life. Like the expanded is to ensure that obviously you can get it over what you're trying to cover, but the recovered is what actually do the actual real work to protect your splice in the real world. On the length side, this is important as well because most drawings come with, let's use a standard 50 millimeter length of tubing. The reason why that's not necessarily the case in all times, if we start having a larger splice, 50 millimeters, even though it may cover the nugget itself, may not be long enough to have enough adhesive to flow in and fill up the gaps. There's also something else called linear shrink. What that is when you expand the tube, there's an inherent shortening of the tubing, let's say, when you recover it. So the whole idea is to kind of take that into account as well when you're trying to select the splice that you need. So understand the typical linear shrink that's specified is about 10%. That's just a nice number. The reality of the situation is it can be 0%. It can even grow sometimes depending on how it's done. But we need to take into consideration that and talk with your supplier or the engineer to understand, to make sure they understand kind of what we're talking about. Because at the end of the day, if you design for 10% linear shrink and you keep getting product that has 20%, you're going to be in trouble, and we're going to hear about it. So we just need to make sure we understand, all that's communicated properly as to kind of what that specific tube, some of the linear shrink is going to be, because some of them you just cannot get 10% based on you going through the manufacturing process. Sometimes it's going to be a little bit longer. Yeah, so that's the typical for caps, where we talk about end splices. It matters, but it matters a little bit less. It matters mostly when we're talking about having an end splice where you have a large amount of wires that you're going to cover, and we call it milk off. It's kind of where you put the tube in and you shrink it down and it just kind of slides off. so that matters as well for end caps especially. So and a lot of it has to do more with the type of adhesive that's in that cap, because sometimes we use a tubing that was designed for splice sealing to make a cap, and splice sealing, the adhesive is designed in such a way to be lower viscosity, so we can get it between those wires like we talked about. And if you put them in the cap, then you put some heat on, it's just going to slide off because it's just not, viscosity is not high enough. With regards to installation, one of the things that we try to do is to center the tube in itself over both sides of the splice. The reason for that is just because we're trying to ensure that we have the same amount of adhesive on both sides and things are nice and balanced and it's easy. It's a little bit, first of all, it's more aesthetically pleasing, and at the end of the day, it just provides like better protection if we can balance everything. Because again, the whole idea is to try and be as balanced as we possibly can. There are instances though where the splice is designed in such a way where you cannot put the heat shrink over the tubing and make sure it's equal on both sides. So what you want to do is kind of offset the tubing itself a little bit to the larger side. And like we talked a minute ago about milk off, when you shrink it down, it might slide a little bit to the smaller side, but where you're going to end up is with the tubing kind of being in the middle. So that's one trick that we use to kind of ensure that if the splice is unbalanced, we kind of put the tubing over here, have it slide a little bit, and then it kind of sits in the middle and provide the protection that we need. And other things on balanced splices, the goal is really not to have them if we can avoid it. But again, if we must have them, we kind of have to think a little bit more to ensure that we protect them. The temperature of your shrink equipment, the time, those things matters. The real value here with your temperature is we don't want to get into burning and scorching and all those things of the tubing itself. But we also have to have enough temperature and time and dwell time to ensure the adhesive melts and flows and does all the things that we needed to do. So it can be a delicate balance. The big thing here, though, is to have equipment supply that's really, really good, because I've seen equipment where, you have like what we call a toaster oven. Left side is 100 degrees, the right side is 300 degrees in that same oven. And there's no way, with that kind of, you need consistency in the oven to ensure that you get the same thing. The moral of the story is we really got to keep paying attention. We're going to calibrate our ovens. We've got to do all the things that we need to do, let's say on a daily, weekly basis to ensure, our QC, we do our first off every day. We check in the middle of our shift. We do all those kind of things to ensure that, we're still getting what we need all the time. I know we use heat guns and those kind of things. I would strongly suggest if we don't need to use them and we can use ovens, that would be better, just because we have better control over an oven versus a heat gun. Direct flame, those are more for heavier wall tubing. Those are like more the electrical world. So we try not to use direct flame and harness splices, let's say, just because, again, we're going to, and especially if we have PVC cables, it's just going to burn. So those are little considerations that we got to take into when we're doing our installation. We get adhesive dripping as well. In your ovens, those might cause fire sometimes, depending on the adhesive, so we got to pay attention to those kind of things. So these are little things that when we're going through our design and in our manufacturing plant and all the things that we're doing, just to kind of say, okay, this may happen, how do we, set up our oven, set up our process, all the things that we need to ensure that we don't have some of these things happen. Let's talk about time and temperature. Typically, if you get a data sheet or a drawing for a heat shrink, it's going to tell you what the operating temperature is and the shrink temperature and all those kind of things. When you set up your ovens, depending on the tubing itself, it could be anywhere from, in terms of the shrink temperature of the tubing inside the oven, anywhere from 80 to 220 degrees Celsius. It is hot sometimes, but again, it depends on the tubing and to make sure the adhesive flows and do all the things you want to do. When you set up your heat source, it could be like your set temperature could be anything from 300 to 600 degrees Celsius. Again, these numbers can be high. There are some manufacturers who set their ovens not to go over a certain temperature. The problem those present is as someone in a factory trying to get tubing or to work is like, because they kind of put a limit onto some of the things that you want to do, it becomes more difficult to actually try and override their programs and those kind of things. So those are little things that we kind of have to think about. We have to make sure with the temperature and time, like they have to kind of work together. And higher temperature sometimes means faster processing, but it also comes with drawbacks like burning your tubing or your insulation, all those kind of things. Obviously, slower temperature, we know that's money. Slower temperature and longer time, we know that's money. It's because you're taking a lot longer to go through. So we just have to balance the entire thing. Factors that affect those things, we're talking about the tubing size, talking about the wall thicknesses that you want to recover to, talking about the wire count. Another thing that's important too is like when we have a really big splice, large cables on both sides, we have heat sink that takes place. What that is when you start shrinking the tube down with your oven, you have this big old metal copper nugget at the bottom and that's just sucking away the heat. So we have to pay attention to that as well. And the reason why that's important in terms of the heat sink is because if the tubing can't handle the temperature required, at some point you're going to start burning the tubing, your splice is not sealed, and you're going to go, what the heck is going on? So we really got to pay attention to the size of the nugget that we have and understand some of the thermodynamics and some of the things that's taking place with regards to just shrinking down and sealing that splice. And like we talked about, we would pay attention to like run rates and your manufacturing speeds and all those kind of things. So that's kind of like the basic stuff. We also have special cases. The special cases are instances where we got, for example, a splice like this, where we just have a shitload of cables. And we talk to the OE or the designer and they go, hey man, there's nothing we can do. And you're mandated as the harness manufacturer to ensure that this thing is sealed. So what do you do? Because if you go get a piece of heat shrink, stick it over it, more than likely it's not going to seal it up just because we just don't have enough gaps like we talked about in these areas to get the adhesive in there to fill it up. So what do we do? So this is kind of, and it can be a splice, it can be a terminal, it can be anything. And here's something that's kind of interesting with these eyelets as well. If we notice, we have these collars here on this thing. The problem with those collars is we can put enhancers in here, and then if you look at the amount of splices come out the back end, is like to seal that's a bear. That's extremely difficult. Like I've seen systems that kind of work to a point, and if you marry the heat and all those things together, they kind of work okay. The bigger challenge though is we just don't have enough, and then if we start getting the adhesive to really flow, then we're going to start to get it to flow right into our eyelet, so now we start affecting our contact point. So all those are really challenges that we run into. So how we do this, we have to figure out a way to get some form of enhancer to do it. And enhancers can be anything from mastics, it can be anything from liquids. I've seen where we have mastics and adhesive mixed together. There's a lot of different things that's tried. The bottom line is it's extremely difficult, and this is kind of when we really need to work with our heat shrink supplier, because for the most part, all the suppliers have enhancers that we can use to help with these kind of situations. Then we run into splices, terminals, and connectors like these. Like, what do you do with these things? Again, it's one of those things where, as a harness manufacturer, we got to think outside the box. The big thing here with something like this is we got to start working on ensuring that we try and reduce some of these, we call them flyers, or those strands that's sticking out, figure out a way to reduce those. I've seen where we put solders and all kinds of things and those kind of things, they help. The problem with those, though, is just kind of make the area so much stiffer, so you don't have the strain relief and some of the things that you need to do. But at the end of the day, though, we got to figure out a way to use an enhancer, again, to help solve some of these problems. Like we talked about, enhancers can be mastics. There's one product that we provide. It's acrylic masks. It's kind of like a mastic. It works like a mastic. The difference here, though, is the temperature ratings. We can much higher temperature ratings. It's a lot more tacky. You don't have to worry about some of the, I don't want to say off-gassing, but as you know, with if we think of a mastic, it's more like a roofing type of a product. And over time, some of the volatiles come off. It just gets driven off just by heat and temperature. So over time, it becomes a little bit more brittle, breaks off a little bit more. Like mastics are pretty good for the most part, but at the end of the day, there are better options out there. And an acrylic mask adhesive like this has proven to be a lot more durable in these kind of situations. And kind of this is what we're talking about in terms of, again, trying to use the enhancer to fill some of the gaps that we run into when we start getting into the weird, big, uneven type splices. This is just some more instances of, where you have a terminal. And the bigger issues that we've seen to run into for the most part is terminals. And the trend in the industry right now is the fact that we're all going to some form of electric vehicle type of a setup. We really got to start really protecting our electronics even more in the computers and all this stuff. So we got to figure, and terminals are just one of the biggest areas where we have water or moisture and those kind of things traveling to the back end of those kind of things. So from what I know, there's a huge push to ensure that we seal up as many of these terminals as we possibly can. Just again, to protect the back end of all the sensors and all the things that go into all these electric vehicles. So it's really a big deal. So this is what I was talking a little bit about, the acrylic mass sealant. Basically, you can still use it with terminals, you can still use it with splices, you can use it for longitudinal water blocking as well. You can stick it beneath a grommet, you can put a piece of heat shrink over it, you can do all those kind of things. But the good news here, again, is always pliable. We don't have to worry about some of the things that comes with mastic. Mastic is widely used right now, which are pretty good. Because like I've been around it, I've seen it, they're pretty good. But again, they have their limitations just like most products, and this kind of take you to another level. And we talk about we don't have to worry about, some of the off-gassing and some of the things that occur with mastics. The next thing I wanted to quickly touch on with regards to enhancers, there are liquid sealants out there. I see some of my old colleagues in the back yelling at me. I know they want to ask questions, but we have liquid sealants as well. The liquid sealants are interesting, and these you can actually literally, put a drop on your splice, and it wicks up inside the jacket and seal up the splice for you. There are some limitations to this in terms of size and in terms of causing the splice itself to become a little bit more stiffer than we'd like. But we know there are certain cable size that it works perfectly on. So there's a sweet spot. And the good news is for the cable sizes that it works perfectly on, it's kind of the most of the splices are, because we're talking about up to about, 10 gauge. Those are the sweet spot. And most splices are in that up to that 10 gauge, maybe 8 gauge size range. Once we start getting bigger than that, we're starting to get into battery cables and all the other stuff, and heavy truck and bus and all those kind of things. So it kind of matters, but it kind of doesn't matter if we're in that sweet spot. So we kind of spend more time in the sweet spot versus trying to go out of it with this application. But and this can be done in a few different ways. Let's see, yeah. So this can be done in a few different ways. There is a needle dropper that we can use to actually put the splice and drop the liquid onto the adhesive, onto the splice, and it just gets wicked up, or you can dip it depending on where it's at. So this is a really, really good way of protecting your larger wires and cables with enhancers outside of the typical mastics and adhesive inserts and all those kind of things. So we've gone through trying to ensure that we can, we'll have questions later. We've gone through trying to figure out a way to make sure we make good splices. The last part of what I wanted to touch on is we need to validate these splices. And there are a couple of different ways of doing it, and these are just typical standard things. There's nothing special about this in terms of what Eurotech does. It's just what's in the OEM spec or the QC spec that the plant uses, or someone like yourself uses. So basically, it's just an air pressure test, leakage test. So essentially, what you do is you get one end of a splice, you get two ends of a splice in water. Get some a pressure tester to ensure that you can maintain 5 bars, blow the air through it for a few seconds, 15, 20 seconds, 30 seconds, up to a minute sometimes, and to check to see if bubbles are coming through your splices. So it's just a basic bubble test. There's nothing, and those are quick and dirty for QC, and it tells you, and you can use that on a daily basis whenever you get your line and your plant set up to get going. Do a quick bubble test. It tells you what's going on, and you can adjust your process parameters as needed. A little bit more in depth is a current leakage test, and basically what you do, you stick this in a saltwater bath, and essentially is ammeter, attach it to it, and if the splice is unsealed, you're going to create a full circuit. So when you apply your current or your voltage, then you're going to get a reading, just because you create a full voltage if it's unsealed. If it's sealed, you obviously get full insulation. So with full insulation, you will not do that, so you will not get a reading, or a very, very low reading. And there are specific readings that we look for example, less than 0.25 of a microamp. Those are like the typical specs. This is a little bit more in depth than the bubble test, because like this, really, you have to let it sit for sometimes 24 hours just to ensure that we get a full soak, and then this will provide a better indicator of kind of how, if we validate and how our splice is working, our process setups and those kind of things are working. And that's it. So I want to say thank you all very much, and now we can have questions if need be, except for the guys in the back. No questions? Okay, this is awesome. Oh.
So you're talking about the heat sink effect?
Yes.
Like the nugget.
Yes.
I know like preheating the nugget or something would be probably disadvantageous for if you got the heat shrink close to it, but could something like that, special situation prevent improper shrinkage or something like that if you were to keep the shrink away from the nugget, preheat the nugget and pull the shrink up?
No, it wouldn't make much difference at all. It would help a little bit. The only thing that the more difficult part is just trying to get the tubing over the hot nugget, and the safety involved. But outside of that, it wouldn't matter.
Okay, thank you.
Yes.
Can you comment a bit on the material selection for shrink tubing? I know you can have polyolefins or fluoropolymers for various applications. Can you just comment a little bit?
Yeah, polyolefins are standard, and they're typically what we use, let's say, for up to 150-degree operating temperature. Once we start getting into the non-poly stuff, so we're talking about Kynar, those are mostly for higher temperature. The other challenge too with a non-poly is it's hard to get an adhesive into the tubing for non-poly stuff. So if you're going to use a non-poly type tubing for your application and you're trying to seal, then you have to use some enhancer. You have to use maybe a mastic or something else. But to put an adhesive into a non-poly tubing is extremely difficult. As a matter of fact, you can't find anything out there right now. Does that answer your question?
Yes.
Okay, perfect. Anything else? Okay. Well, thank you all very much for taking an hour of your day to hang out with me. Hopefully I said something that was at least helpful in what you do on a daily basis. And yeah, thank you all a lot for your time.